Alright, this is part 2 of lesson 2.3, using indirect measurement. Now we're going to take a look at the mirror method. So once again, let's go ahead and say we are trying to find the height of a tree. But instead of using a shadow, we're going to go ahead and place a mirror. That's our mirror. And then have a person stand looking into the mirror so that they see the reflection. In the reflection of the mirror, they see the very top of the tree. And what that creates is, once again, two similar triangles. So this will be 90 degrees. This is the distance to the mirror, right? And this would be the height of the person's eyes, since they're looking down at the mirror. So this is going to be their height. But it's not their total height, not to the top of their head, but the height to the eyes. Height to the eyes. And of course this is distance to the center of the mirror. This is also distance. And then this is the height of the tree. And so in this situation, you're creating two similar triangles again. Light reflects at the same angle off a mirror that it hits, so when you look down, what you see is the same. Whatever you see is at the same angle of reflection as what you were looking down at. So these angles are congruent. These angles are both 90 degrees, which means these angles here are also the same. So you do get similar triangles. And so we're going to set this up. I guess I have to give you some values here, though. In this case, we're going to say this is this distance is 92 inches. The distance a person is from the mirror is 36 inches. So we say this is 36 inches. That's the mirror. And then the height of the person or their eyes is going to be 54 inches. And then we're looking for the height of the tree, which is going to be our variable. So it'll be x over 92, height of the tree over the distance from the tree to the mirror, and then height of the person over the distance the person is from the mirror. So once again, these are both heights, these are both distances. This refers to the tree, this refers to the person. And to clear the fraction, to get x by itself, we just need to multiply by the denominator, which is 92, to both sides. That cancels, and we're left with 54 times 92 divided by 36. When you do all that on a calculator, you'll get 138 inches, or about 11.5 feet. Let's double check the math on that. Let's see, so that is going to be 138 divided by 36. I did something wrong. Oh, I know what I did wrong. It's 138 divided by 12, because that was the total answer. So that's, yeah, it's 11.5. So that's what it winds up being. Alright, and then there's just one more method here. In this method here, we are going to be looking at what we call reflected triangles. And this is good to say if you have like a river or a canyon, something that you can't really cross, but you have people on both sides, you can use what's called the triangle method. So we can pick a point on the bank of the river, edge of the canyon, and we can go parallel to it, 90 degrees. I'm going to put a 90-degree angle there. We can walk down and pick another point. You can then draw a line to this other point across the river and then extend that line and extend this line to create another right triangle. Now this right triangle, they're both right triangles, so they both have 90-degree angles, and these angles are vertical angles, so they're congruent to each other. And since these pairs are congruent, then this last pair of angles must also be congruent, so you've created similar triangles. Now your corresponding sides are your lengths, your horizontal lengths here. So let's say this is 58 feet on this side, and let's say for the small triangle it was 24 feet. And then the distance across is our unknown, that's going to be our x, and then this distance of this vertical line is going to be 48 feet. So we have these lines that are corresponding and these lines that are corresponding, and I once again would build this by triangle and make sure that the corresponding sides are across from each other. So this one is different than the other two in that the proportion isn't as pretty. Like here it was clearly height over distance in our proportions. Here it's going to be just a little bit trickier, but here's our distance across, that's our x, and we'll put the 58 feet underneath it. And here 48 is our distance across and 24 is our horizontal distance. So here it's this 48 over 24, here it's x over 58. So it doesn't quite have the same nice visual representation, but the idea is still the same. This stuff here came from the big triangle, this stuff here came from the little triangle. The horizontal lines is what we put on the bottoms, and the vertical portions of those triangles we put on the top. And now all we have to do is solve the proportion variables in the top, so it's nice and easy. So we can go ahead and multiply both sides by 58. So these will cancel, and we'll wind up with x is equal to 48 times 58 divided by 24. And when you do that, you'll get 116 feet. Now I do want to talk about what if you set up your proportion differently, and each of these problems our variable was in the top. You can always just set them so your variable's in the top. You can do that intentionally. But what if you didn't? What if you went over here and you did 58 divided by x equals, and then you know since 58 is your horizontal, 24 is your horizontal on the small triangle, and x is your vertical here, so 48 is your vertical there, so those are your corresponding sides. Now, how do you solve this to your variables in the denominator? Excuse me, we did this in an earlier lesson when we did proportions, but one easy way to do this is just to flip the proportion. Make it x over 58 and 48 over 24, and now your problem looks like this, and you can solve it like that. So if your variable's in the bottom, just flip both fractions, and then all you have to do is clear that denominator. It's much simpler. Alright, that concludes this lesson.